Hello calculus students, and welcome to a recap of day 2 of our class. So we had just finished quiz 0, which was for participation credit only. If you had managed to correctly bubble in your last name, first name, ASU ID, and special code 8181, which is our course section number. And we went on to start with an intro to changes, because every single day we did a little bit about changes to really start to change our brains about not only thinking about totals, but also about changes. So first I gave you these two problems, and I walked around for a few minutes, and if you want you can pause now to do them yourself. And so of course, if we went from 7 cakes yesterday to 5 cakes today, we have a change of plus 5 cakes. And then what about the change in cakes from today to yesterday? Well, from today, 12 cakes, to 7 cakes yesterday, it went down, so we would have to say the change in cakes is negative 5 cakes. And then we did 2 more sets of problems. Here's the next set. Again, you can pause if you want to practice. And then we went over the answers, which were, if Shelley the cat weighs 16 pounds and then her weight changes by 6 pounds, she must now weigh 23 pounds. And some people asked, well, how do you know if this change right here is an increase or a decrease? And that is exactly why we need to be very clear that our changes have a sign to it. The fact that I wrote a positive 6 here means it is an increase. Otherwise, we have no way of knowing. So you have to always, your changes have to have a sign with them. They have to be positive if it's an increase, negative if it's a decrease. Then, knowing that information, it's pretty easy to do number 4. Bobby the rat weighed 12 ounces, and then his weight changed by negative 3. How much does he weigh now? He now weighs 9 ounces. And I'd like to note that for people, this problem number 4 was easier than this problem number 3. It's as if when you see that negative, you're tuned in to the fact that this is a negative change. But when you see just this plain positive number or whole number, you're not as tuned in to the fact that it's positive. So make sure that you do that for yourself. This is a positive change. Our last set. So for these two examples, I gave you some time to think about them, and then we went over the answers. If Andy counted the number of sausages he had, then he changed that number by negative 5 and 18, how much did he have at the beginning? Well, he lost 5, or perhaps ate 5, and that's when he had 18, so he must have had 23 sausages at the very beginning. Now, number 6 was probably the hardest one of all, because we're used to thinking about time in one direction. But it doesn't matter. We can still think, even though the time goes forward, we can choose to analyze situations going forwards or backwards. So it helps me to draw a timeline. Cameron watched the video running backwards. As she rewound, the water volume changed by 4 ounces. So she's rewinding, and the water in the cup is increasing. Alright, the glass had 6 ounces at the end. How much was in the glass at the beginning? Remember, Cameron started at the end. Well, if she increased by 4 to get to 6, she must have started out when she first pressed play or pressed rewind on the video or DVD. She must have had 2 ounces. Alright, so originally we think about addition, subtraction, multiplication very much as orders to do, right? And that's pretty typical. If your teacher were to write 3 plus 2 on the board, everybody yells out, and I think I asked the class and everyone said 5. Yes, it is 5. That's not wrong. But where's 5 on this equation? Well, 5's right here, but 5 is also right here. 3 plus 2 represents 5 even before we rewrite it. But if we only focus on immediately calculating and evaluating and simplifying something down to a single number, we can't look at what the expression represents even before we simplify it. Right? That has to represent 5. 5 equals 5. And so if we can go from an order to do, when we see these operations, immediately thinking that we have to do something, if we can instead think, oh, this is a way to create a new quantities measurement. Now we can begin to write things down in open expressions, which I'm going to show you what I mean in a second. 3 plus 2 is an open expression. It has not yet been simplified. And then it makes the transition there's two good things about this. The first is that it makes the transition to algebra much easier. The second is that you have in front of you an explanation, a written out series of events for exactly how you made that calculation, so you can look at it. So here's what I mean by that. What is the area of this rectangle? So I gave everyone a second, and they all said, nope, I'm always doing that. And they said that the area of this rectangle is 54. That's very true. Now I want to say this, what about writing it with an open expression? Okay, an open expression leaves all of the procedures and processes that you've done in your head still visible on the paper. How can I dot that I? There we go. All right, so how did we get this area? Well, we did the length times the width, which is exactly what you do for a rectangle. So what is the length of this? Well, since this is a square, all the sides are equal. So is the length 9? Absolutely, the length is 9. It's equally correct to write the length is 6 plus 3. And then, of course, the height of the rectangle is 6. Now, this is still equal to 54. But by writing it out like this, you can already see exactly where everything comes from, right? Showing this answer to someone, for example, would be much more helpful than showing them this answer. And so we're really going to work on understanding the importance and the usefulness of writing open expressions. So now I gave the class this. How long is the orange line segment? Each piece of your expression should represent a new quantity. All right? If I want to go back to here, when I wrote 6, that was the length of the square. When I wrote 6 plus 3, that was the length of the rectangle. And let me just do it. 6 is the height of the rectangle. 6 plus 3, that's the length of the square. And this is the length of the black rectangle. When I add them together, this is the length of the larger rectangle that we're trying to find. And then, of course, the whole thing is the area of the large rectangle. So in the same way, can you find the answer to the next question? So I'm going to clear this answer. How long is the orange line segment? And I gave students about 6 to 8 minutes to work on this. I saw a lot of good answers. I would suggest to you that you should only use these numbers. You should only use the numbers only use 5, 9, and also there is diameter and radius in here, so you can also use the number 2. That's it. That's all you need to answer this. So pause if you need to, because I'm going to go over the answer now. So I'm going to start building this up. I want to find the length of the orange line, which is, of course, right here. Okay, well, I can see there's a right triangle here that I can use Pythagorean theorem on, right? So I can write that if I take this length, this is 9, 9 squared plus the red length. And how do I get the red length? Well, the red length is the radius of the circle. I know the diameter of the circle is 5, so the radius of the circle must be 5 over 2 squared. Alright, so here I'm going to put green. That's the length of the green line. Here I'm going to put red. If I square those and I then add them and square root them, this now is the length of the hypotenuse. The length of hypotenuse. But I don't want the length of the hypotenuse, I only want the orange one, so I'm going to have to subtract out the purple. What's the purple? Well, that's also the radius of the rectangle. So if I minus 5/2 again, this now is the length of the orange line. Length of orange line. So as you can see, every single expression that I created with an operation of adding, subtracting, multiplying, dividing, squaring, square rooting, each one represented a new quantity. Well, I'm writing under my words. And so all of your other homework problems from Chapter 1 and Chapter 2 from Chapter 1 really go into this. Writing an expression that's open, where all the processes can be seen in order to represent new quantities slowly building up to become more and more complicated quantities. Alright, I'm going to clear this work now. And we're going to go on to Shift 3, Thinking with Integers. Thinking with all real numbers. So what happens is, everyone knows how many numbers there are on a number line, right? If I asked you, how many numbers are on a number line? I asked the class and you all responded infinite or infinity. Yes, there are infinite numbers. But being able to answer that question is really different from being able to think, is really different from being able to think with all real numbers. That's what we want. We want you to actually, in every aspect, be able to think with all real numbers. And so now let's go ahead and look at an animation that I have. So let's take this animation and let's imagine that this is the mentality of someone thinking about, oh, this is really zoomed in. Let me zoom out. Otherwise it'll take too long. There we go. Alright. If people really think about sweeping across the number line, they really think this. Sweeping across all the positive and negative integers. I'm going to be generous and hope that we are also talking about negative numbers. And when you ask them to think going across the number line, this is what they do. They jump from one whole number to another. They may be able to answer, oh, there's infinite numbers on the number line, but their mental image doesn't actually have an infinite number of numbers. Now, some people go beyond that. They think of halves, right? We all know people who are comfortable with the fraction 1/2 and not comfortable with any other fractions or decimals. So they can imagine jumping across the number line like this. These are all the numbers on a number line. Or perhaps on a graph, these are all the x values that I should think about. Again, this is not good enough. Let's look at the third option. Let's look at this person. It actually seems to be going across, right? Hitting every number. But if we zoom in and look at this person, we can see what's happening. We can see that this person is actually jumping at 1 every 10th, right? They are thinking about 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, but that's it. They're not really thinking about every single number. Now, contrast that with someone with this mental image of what it means to think about every number. This person, as you can see, is smoothly going through all the numbers available. every single number is passing through their mind because they recognize that in between all of these sections, right? Let's move out. Between -4 and -3, there's an infinite amount of numbers. But if I were to zoom in, there's also an infinite amount of numbers between -0.4 and -0.3. And if I were to zoom in again, there's also an infinite amount of numbers between -0.02 and -0.01. And so you really need to have this smooth image of x going through every single value instead of hopping, right? We don't want an image of hopping. And you can ask, well, why does that really matter? It turns out it really does matter. And you're going to see it coming up later. You're especially going to see it when we talk about constant rate of change. But for right now, we do not want a hopping image of all numbers. We want this smooth, continuous variation going across all the real numbers. Alright, so here is where we actually stopped for today. This was the second day of class, and I will see you in a second in the third day.